So where would you set the threshold more or less in this case? So compare this to this, right? So around 0.5. You can also play around with that threshold and see how it changes things.
For the mask, we can set the image more than the threshold.
Yeah. Yeah, just move this. I just call this object mask. You don't need to export. Yes, you can say that, but you don't need to. Right. So, how's it going? Good, not good. Classroom of fish. Okay, what threshold should I set? 0.5 seems like a reasonable place to start. Okay, how do I define the mask? I want to say all the pixels in image blobs that are bigger than our threshold, right? And then how do I apply the mask? I just multiply my mask by image blobs. And you see I get this mask, and I get this masked image, which is reasonable. Okay? It's not bad. But you do notice that because of the noise I added to the image, you have a lot of kind of what's called salt and pepper noise. So you see black spots in regions that we want to be white and vice versa. And so the way to get around this is to, after I create this mask, while creating this mask, to do some smoothing on the original image. Right? So the smoothing would remove kind of speckly type noise. And so the threshold is set to do the same thing, but we've already learned about Gaussian smoothing, right? So we're going to do a Gaussian filter over image blobs. And we're going to set a relatively small sigma, right? So we just want to remove really small kind of speckle noise. So we're going to set the sigma to be 1. And we're going to say that this needs to be greater than our threshold. And the masked image is in the same way, mask times image blobs. And so you see that by doing this kind of simple operation of kind of cleaning up my data before creating the mask, before deciding on the thresholds, I can get rid of a lot of this speckly salt and pepper noise in my mask and therefore in my image, and I have a true sense of what's foreground and what's background, right? So this is more or less the idea of masking. Now, we're going to talk in a few minutes about how to decide these thresholds and specifically how to do this in an automated way. So you don't have to actually look at your image and decide, oh, this looks like the right threshold and stuff like that for every image. So we're going to talk about that in a little bit. But before that, let's take a little side trip into morphological operations. So morphological operations are kind of a way of manipulating mostly binary images based on shapes. So for instance, if I know that I have things that are spherical or like round in my field of view, I can take this information and work this into my algorithms by saying, okay, I'm going to make kind of spherify everything around that I have to make sure that it makes sense. Now, we can choose the size and the shape of this neighborhood that we're going to look at, and we can kind of decide what we want to get out of it. So sometimes we want to really like take an image and just find very like distinct points, so regions that are very separate. Sometimes we want to take a bunch of regions that seem like they are actually one region and combine them into one region. And this is all done using morphological operations. Now, the most common morphological operations are built on this idea of fits and whether an object fits or hits. So the first thing we're going to do when we kind of define a morphological operation is to define some structural element. So this would be usually a binary image, well, always a binary image, so kind of like a mask that defines kind of the shape of what we're going to look at. So it could be a small disk, or just a square, or something like that. And so let's say this is some image we have in our data. And we want to say, how does this image relate to this morphological element, to this structural element? Okay, so what is exactly fits and what is exactly hits? So let's take the structural element and move it into our image. We're looking at the center of the structural element, okay, so this one. And let's say we put it in here, and our structural element is going to look like this circle. We say that when we put the structural element here, it fits into our image. So every pixel in the structural element overlaps with the pixel in the image, right? So we're going to say that the center of this structural element is going to be preserved. So this is going to stay 1. Right? So if I look at just fitting, this would give me something that looks like everything that is here. Now, if it's like this, what happens? Does this fit? No, right? So this point doesn't work. When the structural element is centered here, it doesn't work. So what do we get? We get kind of the, in this case, something that would look like this, right? So it would make it like narrower, kind of a narrower image of picture of the same thing. So operations that rely on the structural element fitting usually or always shrink your image, your mask. Okay, so everything is going to become kind of more eroded. So this type of operation is called erosion. I'm just going to go around and see all the points that the structural element can fill fully, can fit fully, and this would be erosion. Okay, the other option is something called hitting. So do you have a clue what hitting means? So hitting means every point in space where at least one point of the structural element hits one point of our image. So let's do it in blue. So for instance, this would be hitting. So it needs to be at least 1 point, right? And so this won't be hitting. This is not good. This would be hitting. And the extreme case is like just touching, right? So this would be hit. So what do we get out of hitting? So let's connect all these bits together. So we get dilation, right? We get something that's bigger than our original image. And this is, I'm just going to write down because it's my art skills are. So this is going to be dilation. And this is going to be erosion. I hope I spelled everything right. Right? So you see, and this is more or less the point of everything. You see one effect that dilation often has is that it not only extends the image, it also tends to kind of smoothen it. So you see things that are like kind of relatively small radius like curves kind of get mixed together into more smoother lines, right? And so the most common morphological operations that we usually use for image analysis are erosion and dilation. So for instance, if we get an image of a lot of connected blobs and we want to kind of disconnect them, so we would often do some form of erosion to kind of separate them a little bit more. On the other hand, if we have things that look a bit too speckly, so like we have kind of holes in our data, we would want to do some dilation, right? Close these holes. And so that brings us to these two ideas of opening and closing. So opening is you erode, and then you dilate. So what that does is it removes small regions. So if you have things that are really tiny, it's going to remove them in the erosion phase, and then in the dilation phase, they're not going to come back. So this is good for kind of the speckling and removing kind of noise that's bigger than like single pixel, but it's still like not big features that you care about. Closing is kind of the opposite thing. So closing is dilation followed by erosion, and that is something. So opening would be if you have those small bits, you're gonna erode them into nothing, and then dilate again into nothing. So it removes small bits. Closing is if you have some holes, so you're gonna first dilate. So on the one hand, it's going to close the hole, but it's also going to dilate your whole shape, and then erode to bring it back into a reasonable size. So it kind of acts as kind of just what it's called, like closing of holes. So if you have any holes in your data. Okay, so let's just go ahead and take a few minutes to do this, to do morphological operations. So let's take 5 minutes just for this part. So 1.4.2, okay? So the first thing you need to do is to define the structuring element. I'm asking you to define a disk of radius 10. Notice that I imported this morphological object called disk, and I also imported this morphological operations called erosion, dilation, opening, and closing. So this should probably give you at least a clue on how to do it. And if you want to read a very, 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 very long document about morphological operations, you can follow this link and look at these things. Very thorough. Okay, 5 minutes. Yeah, of course. So you can, it didn't give a link. So you can go to SKI image morphology. And if you can see that there are other, just look for structuring element, and it will give you, you have ball, you have cube, you have diamond, disk, all sorts of things. So you can use whatever one you want. So for instance, if you know your data has like, it has like sharp ends, like you're analyzing crystals, then you wouldn't want to use a circular structure element because you're going to remove all the these sharp features. So this kind of depends on what you're looking at. This thing is not big enough. There's no room for anything. So if you finish this experiment with other structured elements, see what it look like, see if, how the size matters. You can also look up maybe other types of morphological operations. Just to play around with stuff, see what it does.
Also for opening, it first is in and then it really, yeah, well, open, because it should first erode it and then.
Yes.
And also for hitting, it should hit the original limit at least in 1 point.
At least 1 point. So anywhere that hits at least 1 point.
So if you don't deal with the noise, then you have problem.
So there are different ways of dealing with this like noise. So
take the pixels of noises.
yeah, exactly. So it can like expand them, and you also see how this type of noise, like salt and pepper noise, neither of these approaches on its own would work. You kind of would have to do both in some level. So if you just do erosion, you're going to get rid of bright things that are on a dark background. If you do the opposite, you're going to get rid of the dark things on a bright background, but you're not going to get rid of both. All right, so we'll do this, and then we're going to go take a break. Okay, so we want to define a structuring element. We said we're going to use a disk. So we just call a function called disk. And the function has one input, and that input is the size of the disk. Okay. Erosion is simply done by calling the function erosion. This function has two inputs. One is our mask, and one is our structuring element. So I don't know if I said that clearly enough, but all these morphological operations are things you do to masks. You do it to binary images, right? So this is not something you would usually do to a grayscale image, because the idea of hitting and fitting doesn't really make that much sense there, because it's scale. It mostly makes sense, or usually makes sense, to do this when you're working with binary images like masks. Okay, dilation. Opening. And closing. Okay, so you can see how each one of these, what each one of these things did. So you see how erosion kind of took away a lot of our white regions, so it kind of eroded them, but it also makes it maybe easier for us to tell that maybe this and this are two different objects and not just one object that we found it's connected. Dilation does the opposite, so it takes things that seem you don't know if they're connected, and it makes them more connected, and sometimes that's useful. Opening, you see how it removes. I mean, we don't have too many small bright regions here, but for instance, closing, you see how, for instance, this hole, these two holes are disappeared here. Right? It's kind of as advertised, and of course, this is a very simple image. In realistic images, it has a more kind of more striking effect.
What's the new hole that's created
Where?
up there on the closing on the right? The closing one.
Here.
Yeah, that one.
So what happened is that the opening stage, right? So sorry, the dilation stage connected this and this, and then the erosion stage wasn't erody enough to get rid of it. Okay, so what we're going to do after the break is kind of start going into actual data. We're going to look at microscopy, fluorescent data, data of fluorescent nuclei. And we're going to start seeing how all of what we've talked about over the last 4 hours, I guess, applies to real world data. And more so, we're going to go into kind of automation of picking thresholds and stuff like that. That's very important if we start scaling up our data. So let's take 10 minutes. Okay. Questions? Yeah.
If you're using the mask, if you're using this the closing operation on mask, wouldn't you most, especially since I think you use the Gaussian mask, on this component, wouldn't it already mostly be closed off anyways at that point?
So what we use is a Gaussian with a very narrow kernel. So all we got rid of is like really small like speckles of noise. But in, for instance, real data, sometimes you'd have large cells, and you have smaller cell bits that flow off during, let's say, apoptosis. And usually you don't care to analyze the floating around of small bits. Right? And so morphological opening would, for instance, get rid of these things, whereas just Gaussian smoothing, they're still big and they're not like single pixel. They're some circle. So definitely these things are designed to work together. It's not just, and you can use a wider Gaussian filter, and then that would give you some response to a wider, like just to wider cells, for instance, and stuff like that. But yeah, these are not mutually exclusive techniques. Okay. Oh, yeah, sorry.
Oh, I just had an issue with I don't know, I had something.
Okay, so let's do this during the next 10 minutes. Cool.
I was working for this family, the counter, this there, and then I
Sometimes. So sometimes
okay. So can I just
so you
run all?
in here, this is probably some of the not prime.
Thank you.
So yeah, you can just restart the current system, the thing that's doing the calculation. You said you had these like different, are these images of the same eye? Yeah.
Yes.
Same eye, just two different machines. So you can use something called elastic. Really, what you're describing is like what's called registration. It's image.
Yeah, we actually did the registration.
But you said like there were two different scales, and you needed to make them the same scale.
Yes, the only difference was not in was that like so one of the machines rotates, the other one doesn't.
Okay.
Yeah, the only thing we had to do for we just
Yeah.
doing the registers based on like rotation, so that we want to do like pixel like.
Okay.
So that was the only thing that we did for it. And
But there's also scaling.
yeah, the scaling, yeah, it's different for them.
So that's something.
So let me first show you. Yeah. Yes. Yeah, yeah. Yeah, yeah. I can just show you everything. Also,
Yeah, for free. You have enough data?
Yeah. Yes.
Okay, that's not unreasonable. It's also easy for them to get some.
Yeah. So
Let's sit down. Like let's set up a sit down. But we also, particularly, we also do work with eyes. Right?
oh yeah.
So we work on corneas.
Oh really?
Most ophthalmologists don't care about it.
Yeah.
But our models is cornea.
I'm gonna take you to the back of it.
Yeah.
It's
They're more interesting.
I think it's more interesting because most of the images of the eye are focused.
Yeah.
It's
Very things. It's just an epithelium.
yeah, no, it's the color doing a spinal microscopy for it.
Anyway, let's set up a meeting.
Sure, of course we'll do it. Thank you. As you know.
All right, let's begin or continue. So far, everything we've done was we're using kind of test images or artificial data, right? And from this point onwards, we're going to start working with actual data. So these would be microscopy images of HeLa cells that were treated with something. Doesn't matter for our purposes. These data should be already on your computer. They're part of the GitHub thing that you downloaded yesterday or never downloaded it. So they should be already there. So the first thing we're going to do is just to load this data. Now I'm using this function here called image as float. All this function does is it rescales the image. So it takes any integer type image. So I think this one is 8-bit, but I'm not sure it could be 16. And it just rescales it to values between 0 and 1. The reason for that is that it's often easier to work with floats, so with numbers between 0 and 1, than it is to work with integers, because integers have the unpleasant effect of if you divide things by things and they suddenly disappear and stuff like that. So we're gonna use that function. You can also just rescale by hand if you really want to. You can just convert things to float and just rescale. So both of these things work equally well. We use this function imread, which is a part of matplotlib's image module. And what this function does is reads images, not shocking. There are other ways to read images through using other packages. So I saw someone here using PIL. So PIL stands for Python Imaging Library. And they have an image reader there. I think OpenCV has image readers. This is not a unique feature of this package. And all we're going to do first is just load this image and show it. So let's do this. This should run. And you already see that real data looks much more complex than fake data. So one thing you can see is, for instance, these little tiny blibs here that we probably don't want to assume are cells. You can see that some cells are very bright, whereas others are very dim. And this is a relatively good image. So this is an image that is, as far as microscopy data is concerned, this is relatively easy data to process. And even here you see like big differences in intensity, big differences in density. So some regions are very dense and some regions are not so dense. And so these are kind of more realistic things that happen in data. I think this cell just went through mitosis, which is nice for him or her. Yeah, so this is the data. And the first thing we're going to do, you're going to do, is do what we did before. So we're going to, by hand, plot the histogram, find a threshold, put the threshold. This wasn't supposed to be here. Pick a value by I and apply it and make a mask and see how this mask, what this mask looks like compared to your data. All right. So let's take a few minutes for that. So make a histogram, pick a value, and then plot the mask that you get with the value you picked. You can go up to how we plotted the histogram before. You should have an example, and you should just be able to kind of copy and paste and just change some names. Sorry, I picked the threshold for you. You can play around with it. What? It's so you know how when I plot when we plot the histogram, I use this function flatten. So what flattening does is it takes our image, which is some few hundred by few hundred pixels, and it makes it one single vector, and then it uses this and it calculates it. If you don't do that, then it treats every column in your image as its own separate vector. And then it tries to plot the histogram for 500 different vectors. And then it can easily get stuck because a lot of calculations. And so this like flattening is actually important here because it just makes it so that you can figure it out. And also, we want to look at the entire image. So all the pixels in the image, not every line on its own. Okay, so that's the point of this flatten function. And it's just because different implementations of histograms assume different inputs. And this one doesn't know, which is surprising given that it's a part of an imaging package, that it's supposed to get an image. A more reasonable implementation would have been to assume that whatever input is given, if it's two-dimensional, then it's an image, and then we should flatten it automatically. But this is the joys of open code.
So we'll just hit the comment stop.
Yeah, so we can probably stop and keep going from there. Sometimes just the kernel will get stuck completely, and then you need to restart the kernel. The thing on your computer that's calculating this particular thing.
Increase the number of the threshold, the more the mask will be lighter.
Yeah, right. So you're including less and less pixels in your mask. Lighter, darker. Right, as you increase the threshold, you and you decrease. Yeah. All right. So let's do this thing. So we said we want to hist of image nuclei dot flatten, and let's take again 250 bins. And so right away you see that this is not as simple as, where was it? This, right? You don't have very clear two easy to discern peaks, right? And this is a more common occurrence. And so I supply the threshold and also asked you to find one. 0.003 seems like a good threshold, and the mask would be what? So the simplest thing is just to say image nuclei larger than the threshold, right? And you see that this is pretty good. We could have done some cleaning up, like smoothing before we apply the mask, but here it doesn't seem that necessary. And you see that the masked image compared to the original image, so we removed a lot of these like background pixels that we don't care about. But that's nice. That worked fairly well. We have like this is good. But so what's again, what's the problem with just doing this every time?
This takes time.
Well, no. So I mean, we could remove some noise by doing what we did before with smoothing, right? Which would make it slightly better. But let's keep it simple for now. If we needed to plot a histogram and pick a value by I 7,000 times, and then this would be a problem, right? Because we would get very frustrated after a while, and then we'd run out of coffee, and then we'll go home. And so what we're going to try and do is to come up with some more automated algorithmic ways of finding these thresholds. And so over the years, many algorithms have been developed for finding these thresholds. And there is no silver bullet in the sense that there is no one algorithm that works for everything. Maybe with deep learning, I'm wrong now, but for the most part, there is no one algorithm that is good for everything. And so there is a reason for this abundance of algorithms, and the reason is that they are each good for different situations. And so we're going to go over 3 very common ones that 3.5. So one of them is a variant of the other. So the first one is called iterative mean thresholding. This is actually what you get if you ever use ImageJ and you push auto. So this is what it does. So this is how it picks the threshold. What it does is you start off with some random number ti. So this is the black line here. What do you think about my animation? I'm very proud of it. So it starts off with some value ti, and it just calculates the mean of whatever is on the left of ti and the mean of whatever is on the right of ti. Right? So, and everything on the left is going to have one mean and another mean, and then it's going to update this number, this threshold, to be the average of these 2 means, right? And it's going to repeat this until the algorithm converges. So it's going to keep updating until t doesn't move anymore. Cool? So this is a very simple algorithm. It has to converge. These are both positive numbers. You can keep moving until they stop changing. And so background and foreground. So the idea is that everything below t is background and everything above t is foreground. Everything to the left of t is background and to the right of t is foreground. And so you keep doing that until you converge. So this is a very simple algorithm, really easy to implement on your own, like you see here. And it's also implemented in different packages. Okay, the next algorithm, and this is a very popular algorithm that's used heavily in almost all fields, is what's called the Otsu algorithm. The way the Otsu algorithm works is kind of somewhat similar to, let me just explain how it works. Basically, what you do is you calculate for every position of your threshold the difference in variance between these 2 classes. So basically, how much of the variance do you count for by separating these things into 2 classes? So let's say right here I have this distribution and this distribution. Right? It's clear that these are 2 separate things. At every position, there is a total variance of this whole distribution. Right? At every position here, I can say, okay, let's look at this position. How much of the variance is coming from this and how much of the variance is coming from this? There's going to be a point where just the separation is going to provide as much, is going to account for as much variance as possible. And this is the point where I'm going to set my threshold. Right? So I want to say, what is the point where separating them here makes them as discernible as possible? Cool. Now, Otsu is rigorous, so it calculates this value at every point, and then just picks the maximum point. Okay. So you actually go through all of them, calculate everything. Now, luckily, there is kind of cute little math trick that allows you to not have to calculate variances at every position, and you can instead calculate just means. So you can go on Wikipedia and see that trick, but it makes it, calculating means is much simpler than calculating variances. So you can go and see exactly this transition, but it is rigorous, so it's always going to give you the same number. Now the third.
So when you're saying, okay, like where the maximum variance is,
it's kind of explained variance, right? So the maximum explained variance by having this line.
So you're looking at the two sides of that maximum line,
Yeah.
and then you're saying the variance on this side.
The variance on this side, the variance on this side. How much does this different? Like just separating them like this explains the total variance in the population. And where it explains the maximum variance in the population, in the population of pixels in this case, that's the place where I'm going to say this is my threshold. Okay, now the third method is also a very simple method. Strangely, this method is like from the 90s or something, and it's called triangle thresholding. The way it's done is you draw a line between the peak of your distribution and the maximum of your distribution, just a straight line, okay? And then you find the distance between this line and this, like if you take, yeah, but it has a word. Perpendicular, yeah. You take a perpendicular line at every point, okay, and you find the point where this line is the maximum distance, and this point is going to be your threshold. So this is a method that's actually really, really good for thresholding images that are mostly background. So if you have mostly background pixels and kind of a tail of bright pixels, it would be very hard to separate them. Maybe I should have said that Otsu is really good at separating if you have two very prominent peaks, like what you have here. You have like a very clear peak of background and a very clear peak of foreground. And Otsu is really good at separating these things. It's not very good at separating these kind of things. So when you have kind of a tail of positive or bright pixels in the background of many, many dark pixels. And this is kind of where triangle thresholding kind of shines. So these are kind of the three things that we're gonna look at. Scikit Images' filters module has a big variety of thresholding algorithms. Okay, and what we're gonna do first is just apply these three things. Okay, so we're gonna apply these three thresholding algorithms. So you should do this in a minute, and then just plot what you get. So draw what you get from each one, and we're going to take, I guess, 10 minutes for that. In these 10 minutes, please also experiment with other algorithms. So you can you can see them in the filters page. Okay, so let's take 10 minutes for that until we're going to get to 1.5.4.
But he's also doing secular.
You can also experiment with that. How changing the number of bits affects the threshold. It does have a default though, I think, so you don't have to. But
It's a default.
I think it does have a default, but
So you don't put anything.
what's the default? 256?
Yeah.
Okay, there you go. But you can play around with how changing the number of bins. How does that happen?
Yeah.
Start there. Start there. Also on tab. So maybe I should have let you know that little secret. So Jupyter notebooks have tab complete. So if you're writing something and you wanna like image and you have like a few images open and you wanna see a list, you know how sometimes I write something like this, and then I do something and I get this list. So if you just push tab, it would give you this list. And if I just do, if I only have one option, then it, so this is called tab complete, and that's a very useful thing.
So the special is the filter threshold.
Again, sorry.
The new filter. The function is called the filter threshold.
Yeah. Something like that. So it's called just threshold mean. Yeah. So iterative mean is just sometimes called mean threshold. So you can probably also go ahead and do, never mind. I'll go through this one with you. All right, so I see that almost all of you are already done. So maybe this is also, I should probably ask. So far, have you generally found the class exercises too easy, too hard, or the kind of okay, it's too much time? Okay, kind of basically there. Okay, good. Okay, so are we ready to go over what's going on here? So we're going to apply these different filters. We're lucky enough to have them already implemented in SK image. Okay, so filters. God. Okay, filters dot. Oh, okay, that's why. Should have told. No one speaks. So threshold mean is the first one we wanted. And we're going to apply this to image nuclei. Right? Otsu is the second one. And triangle is the third one, right? So you can right away see that they're giving you kind of slightly different values. So the threshold that they find are somewhat different. They're not all giving the same thing. So now let's go and look and see which one kind of worked best. What am I missing? Oh, I need to actually calculate things. So mask mean is going to be image nuclei larger than, what did I call it? Thresh. Mean thresh. Right? Mask also is going to be image nuclei larger than Otsu. No? No. I was overly respectful of Mr. Otsu. And this is going to be image nuclei. And then I was also overly respectful of Mr. Try. Okay, so I have these three things. I can draw them out. And first of all, you see that mean thresholding and triangle thresholding actually give us very similar results. And Otsu was kind of the outlier here. The reason for that is because Otsu is particularly bad in these situations where we have kind of a long tail distribution. Now, if we look at the masks themselves, we see where exactly Otsu failed. You see that cells that were a bit dimmer in the original image were kind of like blown into bits after Otsu thresholding. So you can see this here and here, right? Versus triangle and iterative mean that kind of are agreeing with each other in terms of masking, right? Okay, so the last thing we're going to talk about in this, as far as thresholding, is local thresholding, and this is something it's going to be relatively short. We're going to just do it together. So all the methods we saw before kind of assume that the statistics of pixel intensities are uniform across the whole image. So this assumes, for instance, that the illumination is the same across the whole image. It assumes that I don't have a bunch of cells on one side and no cells at all on the other side. And it assumes all these type of things. which might not be the case. So for instance, if you let a very new student in the lab take bright field images and they don't know how to align the color illumination, then they're going to get very different intensity levels in different parts of your image, right? And so the question is there a way to solve this aside from sending them to realign the microscope? And even though I said before that sending them to realign the microscope is usually the best solution, there are also ways to get around uneven illumination and very different statistics in different parts of the image. This idea of local thresholding is actually pretty simple. All we're going to do is we're going to take different regions of the image, and to each one of these regions, we're going to apply Otsu thresholding separately. And then we're kind of just going to smooth over all these thresholds to get kind of a map of thresholds at different regions, right? And so for that, all we need to know is kind of how big of a block we're going to look at. Is it going to be very small? So we assume that there's large variance between positions, or are we going to say, basically, it's like half the picture is one thing, the other half is another thing, so we can just have kind of smoother transition. Like I said before, and thank the good people of SK Image, they actually implemented local thresholding. So, okay, so this is everything we already know. Local thresholding, and it's just called threshold local. Okay, so if I say filters dot threshold local, it's gonna do exactly what I asked it to do. So I'm gonna give it image. So I'm loading here an image that is known. It's kind of a known example of an image with very bad statistics across the image. So you're gonna see it in a second. So image, and I need to give it the block size. So I chose a block size of 81. The block size has to be odd, because it's just the way it's implemented here. And you see how just doing, so this is the original image. You see how the left side of it is much darker than the right side of it. And so just applying a global Otsu threshold gives me very bad results, because the left side is all dark and the right side is nice and bright. What local thresholding does is, instead of having one number that defines the threshold for the whole image, we have basically a matrix of numbers that defines the local threshold at any position. And then to apply this threshold, you do the same thing, only it's done on a single pixel level. So you can see here that this is applying the mask in exactly the same way, or sorry, the threshold in exactly the same way. But now this operation is not image greater than a number, it's image element-wise greater than another image of the threshold. And this is the local threshold map. Does this make sense? Now, what happens if I change this number, let's say to 201? Okay. We have expectations. So 201, I'm basically saying take larger chunks as background, and you see that now I start losing some pixels at the very left, right? So I get more of this noise, but it does depend on exactly your image statistics, right? So there is no one right number for every image. Cool.
Why does the number need to be odd?
So when it applies the filter, if it is even, then it doesn't know what value to assign to each side, because right? So like a 3 by 3, you assign it to the center pixel. A 4 by 4, there is no center pixel. There is like a center region. So you could have done this a bit more elegantly and just do some, the average of the force of the center ones. But they decided to just say, we're going to force you to have it be odd. Okay, So with this, we kind of finished kind of a big, yeah.
Is there a way to make design it so that it can pick the number or be most effective as opposed to estimating 81?
There is. How would you do that? So probably you can actually do something similar to Otsu, right? So like understand how much variance you have for every value of this region. Yeah, so that's something I would try. For the most part, you shouldn't often need to use local thresholding, because local thresholding often means that something is wrong in your position. So, and going and fixing that should be your first priority. Yeah, so it's also like there's a lot of information that's lost in this step. Okay, so any more questions about thresholding? Thresholding is a big topic. So we have basically finished the first big chunk of ideas for this workshop. And this is basically everything that relates to individual pixels, right? So we talked about just single pixel operations. We talked about small neighborhood operations. So kind of how to take into account these neighborhoods. This is what we talked about with filtering. And then we talked about thresholding, which is also effectively a single pixel operation, because you're going to say each pixel, am I going to keep it or am I going to throw it out, right? And so our journey is going to hopefully eventually take us from image to a list of data objects with features, right? So this is where we're going. And this is the next step we're going to take, right? So the next step we're going to take is going to be, okay, now that we know how to separate the foreground from the background, we're going to want to take this foreground and break it up into interesting objects, right? Now, in the case of cells like microscopy or like this kind of microscopy, it's usually going to be individual cells. But more generally, this could be any object around you. It can be like separating a picture into different people. It could be separating different stars. I don't know. So this is generally an important step. And it goes under the name image segmentation. So you're going to take the foreground, the interesting part of your image, you're going to segment it into individual objects. Okay, and so we're going to talk about a bunch of different techniques to achieve this image segmentation. And we'll start off with kind of the simplest idea. And the simplest idea is something just called connected components. So what is connected components? What's this here? Unclear? Oh, this just loads a bunch of things and makes a mask. Okay, so all I did is I reloaded the image of the nuclei. I made a mask based on triangle thresholding, and I applied that mask. So we have something to work with. We have a mask. We have an image of the nuclei. Okay, so what is connected components? Connected components means I'm going to take this mask that I have here, and every contiguous part, I'm going to call it component 1, 2, 3, 4, 5, right? So this is going to be 1, 2, 3, 4. Each one is going to have its own label. This process of taking this mask and separating it into individual objects and just naming each one of them by a number is called labeling, appropriately. And what we get after labeling is something that looks like this. So it's going to be a matrix, right? And each connected component is going to have its own number. So you see all of these things that are different from 0. So 0 is going to be our background, right? So all the things that are different from 0 and are touching each other are going to get a number. So these touch each other and they're 1, and these touch each other and they're 2. This is just separate, like just one pixel that's on and it's not touching anyone, and it's 3. And this is going to be 4, okay? So the way we apply these labels is using the measure module. So open the measure module and see whether you can apply a label. Right? What do you think the name of the function might be? Label. So measure.label, and what does this apply to? So what am I labeling? So labels are always applied to a binary image, right? And so what I'm going to be labeling is the mask. So here I just have the numbers color-coded. Okay. So it goes from a small number here to some large number here, and this is how many all the labels I found. Okay. So now I'm going to ask you to take 5 minutes and just explore what different connected components look like. And so for that, you're going to have to also figure out how to generate a mask of only a single connected component. Right? So take 5 minutes to get from here to 1.4, so 1.5 point. Well, just do the problem with simple CC segmentation. Okay. So how do you take this map of this label mask, like this list of labels, and only create a mask of a single connected component? So I reminded this is the structure of the mask, of the label. So just numbers on a matrix. Yeah. Sorry. So I just stopped it.
So this is stop. Okay. We need to change some number.
Oh, easy to fill up.
I know, because I didn't have this numbers. I don't know.
Oh no, this is, so here it needs to be the actual mask. So the mask based on this, so not just the number, it's the actual mask. Okay, so how do I get a mask of a specific connected component?
Identify the I.
Yeah, so I just take this label matrix, and I say label equals I. And so this is just going to give me 1, right, true, whenever labels, which is just a matrix of numbers, is equal 43. So this is going to be a single connected component number 43, and 0 everywhere else, right? So I can play with this. I can put 10, 12. and this is going to give me the 12th connected component, and so on and so forth. So it's very easy to address individual connected components by just saying labels equals that number. Now, what is the problem with this very simple approach? The problem is that if we have overlapping objects, they're going to get clumped together. So this is, for instance, what we get for connected component number 87. And you see how infinitely many cells got clumped together into one connected component, right? So this is a problem. This is not great. Now, if we have cells that are really well separated, they're kind of taking up space, and they never touch each other, then fine, we can just do that, and we don't need to worry about overlap. But in a more general case, we do have to worry about overlap. So one thing we can try and do, yeah. It shouldn't be random, but it could be that, like, at some point some threshold that you measured was slightly different than mine because you used a different number, and then it would be, it's not random, it's just different. But in general, you can also look at just the mask here, or like the whole thing here, and see how like all of this is connected. Here probably this is more than one cell. All of these are connected. So this is like 87 is not some magic number. It's just like by chance this is the number that was relevant with how I ran it. So you could say, okay, let's try and just kind of fix this using what we learned about morphological elements, right? Or morphological operations. And so we said that to separate things out, we can do some erosion, right? So maybe erosion would be good at kind of moving these things that are barely touching apart. And then I want to kind of conserve some size, so I'm going to like dilate back to a certain degree. Let's see what I get out of this. So, okay, some of them are better. For instance, I think here I rescued this one cell. Here, these were connected, and now they're separate. And again, sometimes this approach can work. Sometimes you can mess around with different morphological operations and get good separation. And this is certainly something to know, and could be a step in pre-processing, for instance. But this is probably not enough to fully segment your entire data set. And so before we move on to watershed segmentation, which is kind of a big subject, we're going to take 10 minutes break. That's also time. Okay, 10 minutes. Of course. Weren't the same size. It doesn't have, so when you do opening or closing, it's going to just take one structure element and do both. But in general, you can do it on like yourself, like the way that here. So you can do opening with one size and closing, or sorry, erosion with one. So Photoshop is more of an image like editing software, so I wouldn't use that, but image share, yeah.
If there's three different backgrounds, so there's no, like you were saying that you have to look all the 7,000 images to see which one is the best threshold.
No, so you would calculate threshold automatically on each image. So if you have an algorithm that does its job, then each image would get its own threshold. So, and this would be part of your pipeline would be, you know, load the image, calculate the threshold, segment individual cells, do something with them, save the results somewhere.
There are so many images to apply this, like in your experiments, because usually in biology you have like 10 or 10, 20, 100, like thousands.
So personally, every data point, time point, in my experiments, is about 30,000 images. Now, it's true that historically, up until maybe 20 years ago, almost all biology was like 10 images. But the newer microscopy techniques generate a lot of data. So whether it's like time lapse, so we have like hundreds of time points that are to analyze.
So then if I have like 20, 30 images, then I will use image J.
So
it's faster and easier, and then if I need for thousands, then
so you can use these both for both. I think another advantage of using doing it programmatically, which you can certainly do it programmatically through ImageJ also, is that it's much easier to track your work and know what you did, and because it's not it's less like point and click things, and so it's much more reproducible because you can just run the exact same algorithm on a different data set, and you're not biasing anything. But yeah, I mean, so for the most part, when I analyze my data, I use a combination of MATLAB or Python and ImageJ. So ImageJ actually has a very good graphical engine. It's very nice to work with.
But then you interact with the ImageJ through Python.
Through Python or through
Yeah. So you call it.
Yeah.
But then it's again analysis, data analysis, which is basically digital processing. So that one is
everything is digital processing. So nothing is done in a
no, but then that is like kind of data analysis. It's you are processing and then
so
analyze what you want.
Yeah. So after I already did the processing, I get some table of interesting features, and on that I can do whatever analysis I want. Yeah. Sure.
It's a Python question.
Mhm.
Here, we're defining this access for all right now. For your access of the images, like which image put where, and how do you really define the numbers?
So the numbers are in the units of the figure.
Yes.
So I first make a figure that's 12 by 8, and then the numbers are from 10% of the 0.1, so 10% into the image in X, and with a width of 40%.
Oh.
From 20% in Y with a width of 40%.
40%.
And then here I start from 60% because I shift it.
So here's going to be like here.
Yeah. So no, it's going to be like 60% in X, right?
Mm-hmm.
Same height in Y, so this is going to be like here. Sorry, here. And 40-40.
Oh, okay.
And so it's just like placing things.
I see.
But the units are the units of normalized to the figure.
Got it. Thank you.
Sure. Just a minor announcement. I won't be able to answer questions after the class today because I'm supposed to be giving a talk. So I'm going to be. I'll also probably try and end like a few minutes before noon. It's like a lab meeting thing, like a multi-lab meeting.
So I have a question because I'm trying to do all of this in my actual images, so I can use it.
Yeah.
So I can so I
Does this work?
yeah. So I loaded.
So this is, I think, it's quantization. Like quantization. So if you're trying to, if you have more, if your image has less gray levels, then you're asking it to bin over. So some of them are going to be empty.
Oh.
And this is the opposite. So some gray levels get lumped up together.
Yeah, when I try to.
So this is mostly applicable to like single channel, because here you're gonna have 3 different. So my image is what?
But I convert it to an.
Yeah,
We can do it, but I mean, it's not useful.
it's not useful. So you're going to need to find 3 thresholds for each color. What is the shape of it? Oh yeah, I just don't know what the shape is. Oh, you did it after. Where did you do it?
I did this before,
Oh, you did.
yes, but I wasn't using that.
So you're just gonna have to do the masking and every channel. It's also you should look at the images exactly and figure out exactly what type of reprocessing. So what exactly is it you're trying to do?
So, okay.
Start. Yeah. Okay, so let's start. And what we'll be talking about in this hour is the idea of watershed-based segmentation and the watershed algorithm. So what is the idea of the watershed algorithm? Okay, so let's take an example. Let's take 2 cells that are, so we already decided that cells that are touching or very close together, or objects that are touching very close together, are a problem for us, right? It's hard for us to separate them. So let's take this example of 2 cells that are touching and very close together. Everything in the background is dark, right? And each one of these is going to be, it's going to have some intensity level, so it's going to look like, one peak and one peak, right? So just because the intensity levels near the center are going to be higher than the side, this looks like an interesting feature. Now, let's for a second just take this creature, this owl, and make a line across its face, and plot what these 2 peaks would look like across this line, so just the profile. So the profile is going to be like kind of a bow, and then 1 peak like this, and then another peak, and then back to low, right? And presumably, we want to find this region. We want to find the point between these two cells that separates them. Right? So there is an algorithm to do it, kind of generally speaking. And the algorithm is based on kind of how mountains and hills and valleys work. It's called the Watershed Algorithm, and it's fairly simple. So what we're going to do is we're going to take this thing. Right now there are peaks. Water doesn't usually go into peaks. So the first thing we're going to do is to invert these peaks. So we're going to make them into dips. Right? And then we're going to take our blue water. We're going to have, there's an industrial plant here that makes green water. So we're going to fill this one with blue water and this one with green water. Okay? So we're going to start filling this one. Okay? Meanwhile, we're going to also start filling this one. And we're going to continue going up, going up, going up. And eventually, the blue water and the green water are going to touch. Right? So there's going to be a point where they start spilling over, this point. Right? And this is actually the point that we care about. Right? So this is the principle behind watershed algorithms. It's this idea of we're going to invert, we're going to fill with water, and we're going to name each separate basin a different name. So I'm going to, the starting point where I started filling up the water is important, right? So I started here. So this is one of my seeds. These are called seeds. And this is another seed. And I'm going to start filling up, and they're going to touch at a certain point. And I'm going to call that point my watershed line. And this algorithm, generally speaking, is applicable in 2, 3, n dimensions, right? So in any number of dimensions, there is no one, clearly one. Okay. So this is more or less the idea. Okay. So this is what I have here. You're going to label the local minima. So this is the algorithm. We're going to label the local minima. This is what we did by saying this is one and this is the other. We're going to just start filling the intensity level. So this is just filling water up to a certain level. And then as soon as they touch, we're going to call this the watershed line that I have here marked in red. Right? And this is going to be the thing that separates them. And then you repeat this basically until all the points in your image are labeled. So you do this segmentation for your entire image, right? So this is a fairly simple algorithm. Questions about this? Yeah.
You're saying the bulk image image. I understand that. So in your shape over there, the middle line is lower than the two sides around it, right? So yeah, they reach each other there.
Yeah.
So the other sides are not labeled.
So,
is that okay?
So in our case, the whole image is the whole image after masking. So after we remove the background. But in general, you can run this even with masking, and then you're just going to have a third, presumably this would go somewhere here. You're going to have a third basin here, and this is going to be another.
And that
region.
little part not being labeled is okay.
What little part? Here? No.
Like
So
that little- the
between
difference in
these
the heights?
two, you're going to keep filling this until they touch.
Oh,
So until these two touch.
so it doesn't pass that line.
No. So once two things touch, that's where you set it the line here. It doesn't. It's not going to
It's
go.
not a full line.
Yeah.
That's good.
It's a nice analogy, but it's almost there. Flowing water analogy. All right. So that's the idea. So let's start by a very simple implementation, right? So let's just take our image and do exactly what we just said. Right? We're going to take our image. So the watershed algorithm is implemented in SKI image morphology, right? So this is where it is, and you can go in there and look it up and see exactly how it's called. So let's go down and watershed, right? So this is watershed. It gets an ND array, right? An image, and it does something to that image. It does this watershed. Okay. So we said that there are a few things we need to do before we can apply the watershed algorithm, right? So what's the one thing we need to do in this case if we're doing it really naively with no other pre-processing? So at least we need to invert our image, right? So please go ahead and invert your image. The way I wrote this, it's every time we're going to do something, it's going to print out both the result from the watershed algorithm and what image did we actually feed the algorithm. So what was the input? Okay, so we will be able to see some patterns emerge. So did it work for you? Is it looking like really good segmentation? Not so much. Yes. Lots of color. That's great. No, it's just because we probably changed what watershed is expecting. Now watershed has a default when it calculates the mark rate on its own. We're going to give it the mark rate too. Download how you're going to do the markers. Don't worry about it. Okay, so we said we're going to invert the image and just feed it into watershed. So the way we do it is by saying watershed of image to watershed, right? And please add the this argument watershed line equal 1. This is just for us to be able to see the lines that it actually finds. It also has the option of just assigning them to one or the other. This is a okay. So what do we get out of this? A lot of color. Right, so this doesn't look like very good segmentation, right? If you look at this, you're not going to be able to do anything. And the question is why? So what exactly happened here? Ideas?
There's also variance that looks like inside of the
Yeah. So the default implementation of Watershed, which is what they do, is that as the markers where it starts, it takes any local minima, right? Any local minima that it finds. This is not true for yours. Yours is smarter. Yours forces you to give its own marker, to give you markers. But data in reality doesn't look like this, right? What does data in reality look like? It looks like this. Right? And what just happened is it took every one of these little minima and made that into its own basin and tried to find the watershed line between all these little bits, right? And this clearly would give you something that looks very much like this guy, right? So this is not good. The other thing we didn't do is we didn't say anything about the mask, right? So we just fed the entire image. And this is to answer your question. If you don't supply any mask, then it's gonna try to do it for everywhere. So background pixels that just were kind of like also in reality just, some variants also got segmented in some strange way into these little bits. And so what is the point that I'm trying to convey here is that watershed segmentation is only a part of a segmentation pipeline. So it's not something that works just you feed an image and you get beautiful segmented stuff. You need to do some pre-processing to bring it to a point where it actually looks like this. So it's smooth, every minimized, well-defined, the background is removed by masking, and so on and so forth. Right? So this is kind of what we're going to learn how to do now. Yeah.
Okay, that watershed line that you have, you said to set to 1.
Yeah.
If you don't put that or set it to 0, then it looks better but different. What is that? I don't really understand what that's doing.
So what I'm plotting here, yeah. So the way I'm plotting these lines, these regions, is you remember when we were talking about edge detection? So I'm just plotting all the edges. So using Sobel filter. Okay. So when I'm not giving this argument watershed line, it just doesn't have it doesn't have a region of 0 between two watershed basins. So when I say watershed line, it's going to give all this 1, all this, let's say 2, and exactly this line is going to get the label 0. When I don't give it, it's going to give 1 and 2, right? Now, these gradients are always going to be relatively small when I don't have the watershed line, right? So it's going to be like 1, 2, 2, 3. It's going to be a small number, so it's going to look kind of more like it worked, but it didn't. It's equally bad. So you can if you remove this. So if you remove the this filter and just plot the labels, you're going to see this thing bad. And with watershed line equals 0, it should look basically equally bad. So it didn't work any better, right? It's just, now it's more full because it doesn't have these 0 lines in there. So this is just a presentation thing. Okay, so the first thing we're going to do is, so how are we going to do this? How are we going to smooth it or like clean it up? So how are you going to smooth an image? We've already learned that. Ideas? Right, we want to get rid of these like very high frequency little bumps. So we learned that yesterday. So like Gaussian smoothing, right? So, we could try and do things like, instead of finding the basins in intensity level, we're going to find them in the gradient. And then we're going to highlight. So this is basically like edge detection. And we're going to find the edges first and then use that as our watershed lines. And then we're going to find kind of these lines. We're not going to touch too much on that right now. And we can supply markers. So we will touch on this. But the point being is that there are many different ways of doing pre-processing to make this algorithm work better. And when you're actually doing it, you need to kind of try out different ways. We're going to try out a few of them. Okay? So the first thing we're going to do is supply our mask, right? So we didn't do anything with the mask that we worked so hard to calculate. So let's do that. So let's, okay, so I guess now you're gonna do some work and we're gonna get from here until, basically until the end of this. So this is gonna be fun times. So I want you to have the excitement of getting good segmentation on your own without overly interrupting you. So let's take 25 minutes to get all the way to 3. Okay, and this is basically adding more pre-processing steps before you do the watershed algorithm. And this should more or less bring us to the end of today, and then tomorrow we will talk about features. So we start going over everything here and see just apply what we've already learned. Yeah. You also have a different algorithm. So some of you might have a different version of SK image, where watershed requires markers. Let me just figure out how.
But even if I add them, it doesn't count.
But you added none.
Yeah, but I think none is the default. It just requires it.
No, so this is, you're looking at the like new
Oh, I see.
one.
Okay.
So the new one has like a default one.
Yeah.
I think it's something like.
They already updated.
Yeah, you can update it by going to like back to terminal and saying conda upgrade or update this, but we know what is their default, right? So the default is, because I do want you guys to do this. I'm lost. This is, I'm going to get there. Okay, so this is what you want to do. So you need to give in markers. The default thing it does is just calculate the local minimum of this or maximum of this, right? And the way you do it is you import this function peak local max, okay? And everyone else is going to need to do this at some point down the line too. So maybe you should also listen. And then you do peak local max of the nuclei. You say index is false, so it returns an image and not just the indices of the peaks of these pixels. And then you label these, and these become your markers. And then when you run it, right? So these are the two lines that you're missing. And then when you run it, you need to add markers equals markers. Right? So further down, this is something we're going to all want to do for our segmentation. Okay. Cool. Good. This is there. Works?
Yeah.
Oh, it wasn't working for me either. I wonder what they choose. So let's scary code for some. But if you get this error where it says that it needs markers, then you need to do this. But we are going to do so. Right? Okay.
Okay, what is it designed for initial prototype?
So it's like to see what you can do, but sort of give you an
So programming never ever starts off with no one programs the idea that programming is to open a blank page.
Yeah.
Just like start writing. Where it's almost always the first thing you have to research for some of the and then we take it and start so don't think that I would never be able to start writing this. This is not the point. The point is that this is not programming. The real world this is a certain mistake. This is true in any level. People are working for Google don't go and every day open a blank piece of paper and start writing code. Well, you put the other people are doing their goals and modifying the speed on the list. Don't let them be
Yeah. Okay.
What do you think? What features are you looking for? So you're looking for segmentation of what?
Oh, we want to remove those backgrounds.
Right. You want to remove all the stuff that's
Yeah.
like, the sigma should be based on your data.
Yes.
Based on what you're trying to get out of it. What are these? These are cells, right?
Cells.
These are cells. And you want to get individual cells. So sigma more is the size of an individual cell. This is the idea. So you're trying to highlight features that are the sizes that you're trying to get out.
Okay, so it should be like as small as possible.
Well, not as small as possible, but cells are pretty big. 30 pixels, like 5, 10 pixels.
Oh,
You're owning an eye, so that's good.
What?
You're owning an eye, so that's good. Also, just try out a few sigmas and see what works. Right? Just try some and see what works. And see. Yeah. So it's just what it's expecting. Okay? So it's expecting things that look like this. If you don't invert the image, it's going to find this as a cell. Right? So it expects the minima to be the where you are, like the centers, and kind of fills up to the maximum. So in terms of like something that looks like this, it's going to find this as a cell and this is a watershed. It's going to be kind of the opposite of what you want. Does that make sense?
But it depends on the image, right?
It depends on.
If the real
So if the image, if the real if in the real image the things you're looking for are darker than your background, then yeah, you're right. It should be. So the point is that like eventually what it's trying to find are features like this. If your original image is features like this, then you're good. If your original image are features that are bright, then you need to invert. Now it's more so there are different implementations of Watershed that invert automatically. So for instance, I think in MATLAB, if we ever do this, you don't need to invert your image because it assumes that the image is like bright but it does the opposite. So notice that when you're supplying the mask, you need to both multiply or like apply the mask to the image, but also there is an argument in Watershed that is mask, and you need to supply that argument to Watershed. Okay. Yep. So you're smoothing out them out. Yeah, that's part of the.
So how can you find that what is the best? It's just something that we are doing manually.
So first of all, yeah, there is a little bit of trial and error, but usually the sigma that you're going to use to smoothen your data is going to be more or less in the order of the features you're looking in the data. So here I used, well, we're going to go over it, but we're looking for cells. The cells are about 8 to 10 pixels diameter, which means like half. So sigma is like half it, right? So it's like 4, 5 pixels, and then you're going to use sigma that's more or less that size. So it really depends on what you're looking for. Again, it's the same impure version of Watershed. don't know which version it is. That's the best way to describe it.
Yes.
Almost like this.
It's working more or less.
Feature extraction.
Yeah, so we're going to go after feature extraction, and in about 3 minutes, I'm going to fill in the parts that need to be filled in, and then we're going to convene for today. So, and at the very end. So, do you want to keep the same markers that you found before smoothing, or no? That's you. So the markers that you found before smoothing are all the little peaks here. You probably don't want to use these. You want to probably find new markers based on the smooth. All right, so let's start filling all these out. So masked image, we know how to mask images. Image nuclei times mask, right? So we know how to do that. Now we're going to invert this image. And finally, we're going to need to actually do the watershed. So watershed of this image. So image to watershed. We're going to ask it to keep the watershed lines. Equals 1. And we're going to also give it the mask. So mask equals mask. Okay, so let's see what we get out of it. Oh, it's my fault. Okay. I'm sorry, it was my fault. Why didn't you tell me it was my fault? So we see we get rid of the background, but we still have a lot of over-segmentation inside the cell. So this is caused by these little, the fact that the data is noisy. So to get rid of this, like we said, we're going to try and smooth this data a little bit. And so what sigma should we pick was a question that was asked a few times. And the answer is that the size of your smoothing needs to be more or less the size of the features you're looking for. We're looking for cells that are about 10 microns wide. So we're going to use a sigma of probably 4 or 5 microns. So that's the half net. So I'm going to put 4 here. And then I'm just going to do the smoothing. So we also know how to do smoothing. So smoothing we do with just Gaussian. So filters dot Gaussian. What are we going to smooth? We're going to smooth our masked image. We're going to use a sigma of sigma for smoothing, right? And then we're going to invert this image, and we're going to take this image and feed it into Watershed with the mask, and we're going to get something, right? So we're getting there. We are still having some over segmentation here and there, but this is already looking much better, right? We have some regions here that didn't look quite right and stuff like that. So the last thing we're going to do is we're going to try and find the local peaks, basically the seeds on our own. Now the way we do it is kind of similar to what we discussed for the people who had faulty or old SK image versions. So we're going to find the local max in these smooth images, And then we're going to look for local maxes that are very close together. So the way we're going to do this is just by dilation. So we're going to take these local maxes and dilate them, right? And once we do that, local maxes that are very close together are going to merge. And hopefully that will get rid of at least some of our over-segmentation issues. So, okay, so what do we have here? We already did all the smoothing. We wanted to define a structuring element. We're going to define a disk with radius 5, so kind of a nice round thing. The peaks is similar to how we found them before. So we're going to use peak local max. So we can usually get a good sense of what we're trying to do from which package or which functions we loaded. So we're going to find the peak local max of our masked image peaks. So this like masked image. Oh, sorry. Oh, I was nice enough to already tell you how to do this part. Right? So this is how we do the peak local max. Then after we have these maxima, we're going to merge them with this disk. So we're going to dilate. And we're going to dilate masked image peaks with this structural element that we just defined. So this would have been a bit annoying for you to do on your own. But this is just, it's the same syntax that you used before. And then to get the markers out of these merged peaks, we're going to say label these peak mask, right? And we're going to have that as our new markers. We're going to use the same image to watershed that we calculated before. And let's see, oh, markers, measure.label. Okay. And look at what we got. So this is the image that we feed in. These are the peaks that we found. So you see here and there are still kind of issues. If you looked at the image by eye, it would be hard for you to tell whether they're just one cell or two cells. So it's the peak of the normal image, and which is the minimum of the inverted image, exactly. You see that, let's say here, these are 4 cells, one after the other, in very close and kind of overlapping, and still we managed to figure out that these are 4 cells. Yeah. Yeah. So we dilate these peaks so that ones that are very close together are going to merge into one, and this kind of will get rid of over-segmentation, which was a problem before, right? So let's say here we had 2 peaks, even though this is clearly 1 cell, and then we managed to merge them into 1 peak after this procedure. And what we end up with is a fairly good segmented image of our cells. You see, it's never perfect when we shouldn't ever expect perfection. But let's say the vast majority of cells here or labels here contain exactly 1 cell. Now, this is a good result of a segmentation, right? So you will never get 100%. Also, because even if you do it by eye, it's hard to get 100%. And if you did this to I don't know, a large stack of data, this would be a very good result to have as your baseline, 90-something% accuracy. So a good way to know that you're in a good, kind of as good as things are going to get is there is always a trade-off between over-segmenting, which means like taking cells and cutting them up into bits, and under-segmenting, which means multiple cells being labeled as a single cell. And a good place to be is when you have the errors you have are not systematically this way or another. So you have a little over-segmentation, a little under-segmentation, but generally speaking, most of them are good. So you can see like under-segmentation here and over-segmentation here, but mostly everything looks pretty good. And so this is where we're going to stop today. Tomorrow is going to be, sadly, our last day, where we're going to talk about feature extraction, which is a good thing to know. So we want to convert our segmented cells into actual information we can use to analyze. And we're going to have a short kind of intro to more modern approaches that people are using these days. So thank you guys for your time, and I'll see you tomorrow.